Oh, I see. Is this frozen? Okay, there we go. All right. Yeah, so I'm going to be breaking down this talk into sort of a couple of different categories. And for those of you who saw this talk at March meeting, there's going to be some overlap, but there's going to be also some new stuff. So I invite you to stay tuned, and we're gonna talk about a lot more recent stuff as well as the headline result about memory experiments. So I want to talk a little bit about the Google roadmap to creating a error-corrected quantum computer. And then we're going to talk a little bit about hardware, but it's going to be very, very quick. We're going to give you an overview of the latest sort of performance that we get on this Willow architecture. And then we're going to talk a little bit about quantum memory below the surface code threshold. This is kind of the big headline results that, that everybody was excited about around December 2024. And then we'll get into some new experiments regarding logical gates and then color code, which I'm very excited about.
Good.
Okay,
good,
so
good.
this is our roadmap to building an error-corrected quantum computer. The idea of these roadmaps, and we present them in all the presentation that we do, but they're really important for two reasons. One, it allows you to break down a big problem, like building an error-corrected quantum computer into smaller, achievable sort of milestone. And two, it keeps track of our progress, right? So we can say, this is the next thing that we're going to be achieving, and you can keep us accountable for this. Where the next thing we're going to be doing is sort of this M3 long-lived logical qubit. But let's talk a little bit about the stuff that we've done so far. The first milestone that we had set for ourselves was to accomplish something that was beyond classical. And the idea here was to run an algorithm, any kind of algorithm, that would be hard to perform on a classical computer. The algorithm that we decided to run was something called random circuit sampling. This is a hard problem for a classical computer to do, but something that's very well tailored for quantum computers to do. And we actually were able to achieve this in 2019, and later on, with later revision of our hardware, we actually reproduced these results in such a way that nowadays, running something on a quantum computer that takes about 5 minutes would take, septillions of years, however many zeros that is, to run on a classical computer. And this is, at this point, it's kind of meaningless how big this number is, but really this is a nice benchmark to show progress that we're making from year to year on the same problem. Then the second milestone that we set for ourselves was to demonstrate the proof of principle that quantum error correction can work. And for this, we essentially build a prototype of the logical qubits. And we published this for the first time around threshold in 2023. And I say around threshold because what we did was to demonstrate that a D5 surface code, and if you're not familiar with these terms, we'll go into more detail on what that is. But if you are familiar, we demonstrated that a D5 surface code could beat a D3 surface code by about 4%. Now, this was a small margin of improvement, but it is sort of a good proof of principle that error correction can work. And indeed, at that time, we said, okay, we're just breaking even right now, but it's going to start getting better. And indeed, the paper that I want to talk about today is this below threshold result that really shows that we're able to sort of perform these quantum error correction experiments now way below threshold. And so that improvement has come. And it's helpful to remind ourselves of this comparison from 2022, and I refer back to it a couple of times because it gives us a point of reference to sort of compare the current results to. Okay, now let's talk a little bit about hardware. For those who are familiar with our hardware, this is going to be not any news, and for those of you who aren't familiar with our hardware, this is going to be too fast for you to learn anything. So I don't know why I'm presenting this at all, but I'm going to do it anyways. Just because it's nice to see what kind of system we're dealing with here. We're dealing with these transmon qubits, which are these superconducting circuits, which have a capacitor in parallel with these Josephson junctions. And the idea is that we can essentially create this potential landscape that gives us different energy levels, and we can use the bottom two energy levels as our qubit. The way this is formed is this big capacitor is essentially this big cross here. So you have a capacitance from this metal plate to the ground plate here, and then you have a small Josephson junction here. In fact, you have two of them that form this little loop, and you can tread some flux in that loop using this flux line here that drives a current in here, that drives a flux in this loop, and that allows you to tune the frequency of your qubit. You can also drive some microwave with this drive line over here that allows you to flip your qubit state from 0 to 1. And then finally, you have this readout resonator that allows you to read out the state of your qubit, whether it's a 0 or 1. It also allows you to do a reset as well. So this is as much as I'm going to talk about transmon qubit in this presentation. But we've iterated on this system many times over, and the latest version of this has been our Willow chip that we announced in December 2024. And as before, we have fast gates, tens of nanoseconds. The reconfigurability part really refers to the ability to tune the frequency of our qubits and the ability to tune the frequency of our couplers. And finally, we have a relatively high connectivity for our qubits. We have a 4-neighbor connectivity, which is high for these types of superconducting qubits. And I couldn't resist putting this fancy image here that is moving and that the Harts department have done there. I love it. It's great. So these are the specs for our latest chip. You can see that the T1 time are quite good if we compare it to what we had before. We have good single qubit gate errors, 2 qubit gate errors. Our cycle times is an important sort of number to keep in mind. It's about 1 microsecond. This is something that's pretty good for a quantum computer of all types. You have different types of implementation, and on superconducting qubit, this is something that we have a good number for, so that's interesting. Cycle time is one measure of the stabilizers. So measuring one set of stabilizers is one cycle time. And so here, if you are interested, you can look at the spec sheet. It's online as well, but it exists, and you'll get a lot more information on what's in there as well. What I've shown in this table is just the means. Of course, we care about more than just the means. We want to see what the whole distribution looks like. This is particularly important because if you have outliers in your system and you're running an experiment on your full processor, this can sort of mess you up. But in this case here, we have very well-behaved distribution, like you can see in these cumulative distributions. And the other thing that you can't necessarily see on this graph, but I'm just going to tell you, is that all these errors are about twice as good as on our latest generation of processor, the last one, which was the Sycamore chips. So we've improved everything by about a factor of 2, and it's still reasonably well behaved, and everything's sort of a smooth distribution that doesn't have too many outliers. So this really tells something about yield in these devices, and this is important for these experiments. Okay, and we were talking about T1 just a second ago. This is why we think that this number is important and is sort of much better than we had over the last couple of years. As you can see, this T1 metric has been pretty flat for us over the last couple of years, but on this later generation of processor, it's really rocketed up by a significant amount, and that's really enabling some of these demonstrations, these quantum error correction demonstrations in particular. These are great to have. Okay, so now let's dig into the actual quantum error correction experiment, and I'm going to specifically be talking about the surface code below threshold. So first of all, why do we need quantum error correction? Well, the reason we need quantum error correction is that although we've made tremendous progress at making these qubits better, when you talk about these physical qubits, you're talking about error rates on the order of about 1e-3 to 1e-4. And this is, again, tremendous progress to where we were 10 years ago, for example. But it's still nowhere near sort of what you need to run a practical algorithm or practical application of quantum computing. And you can imagine that you could improve these physical qubits by some amount. Maybe someday we'll get them to be 10x better than what we have them right now, and that would be amazing. But that doesn't get you anywhere near the regime where you need to be to run these quantum algorithms. And so you really need to have something that bridge this gigantic gap between what's physically realizable with this system and what's practically required to run these quantum algorithms. And the thing that comes to your rescue is quantum error correction, which sort of promises to trade in many, many noisy physical qubits for one excellent logical qubit. And one example of this is the surface code, which is sort of the canonical example that many people have studied over the last couple of years. And in the way that it works is you essentially have a grid of D by D qubits. Got all Chrome River done for now, okay. Yeah, basically, you have this D by D. Okay, if there's a question, Chris will let me know, I'm sure. Okay, so yeah, basically we have this d by d set of qubits, and and basically the idea here is that you have the system behaving in a sort of a redundant fashion to basically protect one degree of freedom, that is your qubit. Now, this idea of quantum error correction only works if you have your physical qubits that are good enough. And we're going to try to define that more carefully. What does good enough mean? Because this is an important caveat. This is kind of the disclosure they put at the bottom of the advertisement, right? And you really want to define what that means. And what it means is basically whether you're below threshold. So that's the conclusion of this slide, but I'm going to walk you through the details here. What you can see on this plot here is the physical error rates on the x-axis, and this is a simulation plot, right? So people have been simulating these since, like, 10 years ago. This is a simulation from Austin Fowler, for example. And what you see on this simulation is the physical error rates on the x-axis, and you see the logical error rates of your overall surface code on the y-axis. And what you can see is that as you reduce the physical error rates, your logical error rates also go down, okay? No surprises there. But what's interesting is that when you increase the code, the distance of your code, you see that you reduce your logical error rates, and you reduce it by this factor of lambda. This is because error correction is working well, and you get this exponential suppression of logical error rates. So this is the regime where quantum error correction is working really well, and that's where you want to be. Unfortunately, if you look at the top of this plot here, you can see that your errors is actually sort of flips around, and now larger code actually perform worse than the smaller code, and this is because you're in a regime where adding more error, there's just too many errors, and the decoder is not able to keep up and sort of figure out what's going on in your experiment, and so adding more qubit just adds more errors, and now you're in trouble. So in between there's sort of a threshold region. Now, all of these lines don't cross exactly at the same point, so it's not really a threshold point. It's kind of a threshold region, but this doesn't really matter. The point is you want to be well below this threshold in the regime where error correction works well. And I'm gonna steal the punch of this whole presentation. We're now below this threshold, and that's what we're really excited about. And note that what's cool about being below this threshold is that if you are there, in theory, you can just keep on adding more qubits, and you can scale your error rates essentially arbitrarily low. And so this is how you can sort of expect to achieve these really, really low sort of error rates that you need for quantum error correction. So that's the goal. Okay, practically, how are we going to demonstrate that we're below threshold? What we're going to do is we're going to compare smaller logical codes to larger ones. And the goal is to demonstrate that we can get better logical error rates on the larger code than we can on the smaller code. So we're going to compare a distance 3 code to a distance 5 code, and then to a distance 7 code. And in theory, the distance 7 code should be able to make up for more errors in the system, although it does require a lot more qubits. And that's kind of the idea. So if that's the case, then we're below threshold. And if that's not the case, then we failed at our task here. So let's see if we can make it happen. Okay, so the experiment that we're going to be doing is a logical memory experiment. And the way that this works is it's pretty simple. We start with initializing all of our qubit in a known state. So we initialize our logical qubit in a state that we know from the get-go. And then we're going to run quantum error correction. So these are these rounds of error correction. So as Paul was saying, these are essentially measuring all the stabilizers in our systems. For every round of this error correction, we're going to measure all of the stabilizers in our system. And we're going to do this for n rounds. And we have essentially n is equal to 3 here, but in our experiments, we'll get an n that is much, much larger than that, and around 250. And at the end of this experiment, we'll measure all of these qubits, and we're going to feed all of these measurements as well as the results of all these stabilizers to our decoder. And the decoder's job is going to be to figure out what happened and tell us what state it thinks this logical qubit is in at the end of the experiment. And so now we're going to have a result that we're in at the end of the experiment. We're going to compare this to the result where we started at the beginning of the experiment. And if those two matches, then we have succeeded at this task of memory. If they're not the same state, then we have failed at this task of memory. And we're going to record how many times we succeed and how many times we fail, and give this experiment a probability of having a logical error. Now, I want to highlight here that logical memory is super important. The reason it's super important is because it's very similar to basically all the computation that you want to do on a quantum computer that's implemented with the surface code. So actually doing a 2-qubit gate with a surface code quantum computer is actually not so different from just doing memory. Essentially, it's just doing memory and adding just some small disturbances to that algorithm. And so if you can do memory well, you can do 2-qubit gate well, you can do Atomar, logical Atomar well, you can do all sorts of sort of moving operation and all that stuff. You can do that all very well as long as you can do this memory experiment well. So this is a real good benchmark to compare experiments from one to the other. Okay, and this is sort of the headline plot here. So we have this is sort of the main plot. If there's one plot to remember from this whole presentation, I would say it's probably this one. So I'm going to spend a little bit of time explaining what's going on here. On the x-axis here, you have the number of rounds of error correction that you're running. So on the previous slide, I was showing 3 rounds. Here we're going up to 250 rounds. This is kind of the amount of time that this memory experiment is lasting. And on the y-axis, you have the amount of error that's been, the logical error that's been accumulating. And so as you can see, as you increase the time of the memory experiment, you get more and more error. This is unfortunate, but it's also unavoidable. What you want is that rate of increase of failures to be as slow as possible. So you want this line to kind of go down, and eventually in a fully protected quantum computer, this line would basically be flat here at the bottom here. And so it's going to slowly come down as we make our hardware better and better. But in our cases, what we want to show is that we have lower errors for our larger distance code than we do for our smaller distance code. And indeed, this is what this plot shows. In red here, these red triangle here show the distance 3 code. And then you have in cyan, the cyan pentagon here shows the distance 5 code. And these blue heptagon, these are heptagon, by the way, not circles, for obvious reasons. And these show the logical error rates for the distance 7 code. And so you can compare all of these rates. So you can fit a rate to all these curves and compare them on this log plot. And what you see is that they form a line, and the slope of that line tells you what the suppression factor lambda is, and that value ends up being 2.14. Which is really, really good. It means every time you increase the size of your code, you reduce your number of error by a factor of 2. Well, this is exponential scaling, right? You have this lambda factor to the distance power, and that's really, really nice. Anytime you have exponential working in your favor, you're in a good place. So, so this is good to have, and then you can sort of do simulation, and you expect this will just keep going as you start adding more and more qubit. So in principle, as far as we know right now, this can go down arbitrarily low. We'll put a caveat to this in a couple of slides, but on looking at this data, it's pretty impressive. Okay, there's 2 more things I want to point out about this plot. First, we have this green line here. That represents the best physical qubits we can find. So we take this array of 105 physical qubits, and we try to figure out the hero, physical qubits in that whole grid, the best one. And we try to run a memory experiment on it. This is essentially a T1 or a T2 experiment for those of you who are familiar with these types of experiments. You can see here, this is how well this lasts. So you can see that when you start implementing this memory experiment, you have a lot of overhead. You're doing all these stabilizer measurements, you're doing all sorts of operations, and that's causing more errors than it's fixing in the beginning. But as you increase the size of your code, you can see that quickly you're going to outperform your physical qubits. So your D7, for example, and even your D5 is now outperforming even the best physical qubit in that ensemble. Now, we don't want to emphasize this too much because we think that this lambda value is actually sort of the most important numbers in this whole chart here. But some people care about this sort of break-even point, and therefore, here it is. We are at break-even on the task of memory, at least. Now, the second thing that I want to point out, and the thing that I'm most excited about on this plot, is actually comparing to these results here. Here you have these gray triangle, which are the D3s, and the black pentagons, which are the D5, for the experiment from 2023. And this was the experiment, remember, where we had about a 4% outperforming of the D5 over the D3. And at the time in 2023, this was a huge result. Everybody was super excited about this result. It was published in Nature. It was state of the art at the time. And now I plot this on this plot here, and it looks ridiculous. It looks really bad. And that really speaks to the amount of progress that have happened just in the last year and a half to 2 years. And so when I look at this, it makes me really, really hopeful about the future. It's like if we only, if we do this a couple more times, we're going to get to a really good place. And so this is my favorite part of this plot for sure. And another point I want to make is that even though the physical qubits were only improved by a factor of 2, because of the exponential factor that quantum error correction gives you, the actual logical error rate that you get between this and this, for example, is up by a factor of 20. Yeah, okay, this is one distance greater, but really you can even compare to this d5 to this d5, and you can see that the error rates are not just a factor of 2 better, but they're going to be a factor of 10 or 20 better, and that's because error correction is giving you these exponential suppression factor. So that's really important to note. You don't have to improve these things by a huge factor for it to make a big difference at a large distance. Okay, another aspect of this experiment I want to talk about is real-time decoding. So this is really important because besides just doing memory, at some point you want to run algorithm. And to run algorithm, you need two things. You need Clifford operations and you need non-Clifford operations. Okay, you need more things. You need measurements and all that stuff. But as far as gate is concerned, you need Clifford operation, you need non-Clifford operation. Clifford operations are pretty easy to do with all these lattice surgery and modification of your topology of your grid. But non-Clifford operations are kind of tricky, and they require you to create these magic states or these T states. And creating those T states itself require that you do some feedback. And doing this feedback requires that you do real-time decoding to figure out what feedback to do on your system. And so at the end of the day, if you want to do non-Clifford gates, which are essential for running quantum algorithms, you need to do real-time decoding. And so, so when we have this this quantum computer, it's going to have a decoder that's running in real time, and it's going to feed back the result to our system that's going to do some operation based on that value. Okay, so the first step to this is to be able to go fast enough with your decoder to do this real-time decoding, and this is what we were able to demonstrate. And when we do these types of systems, we want to be able to characterize a couple of different metrics. Some of them are timing related. For example, you want to be able to meet throughput. This is a hard requirement. This is telling you that if you have X number of measurements that are coming in at every microseconds, you need to be able to process them as they're coming in so that you don't build up a queue or buffer and they don't accumulate sort of delays inside your quantum computer. And so that's a hard delay. You can't fall behind on this one. And indeed, we were able to do this, and we're able to even test this up to 1,000,000 cycle. We can run this decoding algorithm in real time for 1,000,000 cycle, and it never accumulates any delays. And so that's looking pretty good. Now, the second timing requirement is latency. Now, it might be subtle what the difference between throughput and latency is, and I'm not going to go into the details here, but indeed there is a difference, and if you want, we can talk about it later. But this is sort of a soft requirement. It tells you what delay you have between when you receive your measurement and when the decoder spits out an answer for that set of measurements. And this kind of sets the rate at which you can do feedback, and therefore the rate at which you can do these non-Clifford gates. So this is an important number. It's kind of your clock rate for your quantum computer, if you will. So it's an important number. You want this to be as fast as possible, but there's not really a hard number here. And it turns out that in our system, the number that we got here was about 63 microseconds, which is really, really good. And we were quite happy with this. Now, additionally, the other thing that we want is to have this system be accurate. And this is because now that we're processing these things in real time, we have to make some approximation to our decoder algorithm to make it go faster, essentially, right? And we don't want to make so many assumptions that our decoding become inaccurate. We want to keep it accurate even through these approximations. And so what really matters at the end of the day is not the lambda value that I presented on the previous slide, but it's going to be the lambda value that we can achieve with this real-time decoding. And so this is an important number, and indeed, we don't get quite the 2.14 that we got in the previous slide, but we get about 2.0, and that's sufficient. It's close enough, and we're pretty happy with this. And you can see sort of what that translates to in terms of error rates. These yellow dots and red dots here corresponds to the D3 and D5 of a offline decoder. So this is a decoder that has all the time it needs to run decoding. So this, you can do complex sort of decoding algorithms. And in blue here, you have the real-time decoding. And yeah, you can see it's a little worse than these two, but not dramatically so. You can still sort of get away with it, and that's important. Okay. Now it's time to put this caveat on this sort of arbitrarily scaling of errors that I was talking about earlier, and to talk a little bit about repetition code. So repetition code is a different types of error correction code that is sort of quantum error correction in easy mode. And the reason it's sort of easy mode is because instead of having a 2D grid of qubit, what you really have is a line of qubit. And therefore, in the same space where you can implement a D5 surface code, this 5 by 5 square of qubits, you can actually implement a D25 line of qubit. And so you can go to much, much larger distances. And at the same time, the threshold for this code is much higher. Essentially, if you're sort of below, a 50-50 chance of having an error, you're going to, be in a good place for this repetition code. Whereas for one of these surface code, you need to have a much lower error threshold. So you have a higher threshold, which means higher lambda value here of about 8.4, and you have a higher distances. And so you can reach these really, really low error regimes because you have both of these things work in your favor. Now, unfortunately, what we found out in 2023 is that this scaling didn't go on forever and actually started to saturate around this 1e minus 6 value. And this was kind of disappointing, right? You kind of don't want it to saturate around 1e minus 6 because remember, the range that we're targeting here is about 1e minus 9 to 1e minus 12. These are where these applications of quantum computers are staying, and that's not good enough here, right? And the reason that we were seeing this plateau is essentially because of these correlated errors. And I won't go into the details, but essentially quantum error correction codes are good at correcting for independent errors on qubits, but they're not good if your whole chip goes bad at the same time. If everything goes bad at the same time, there's not much you can do about this. There's not enough redundancies for you to do anything about that. And so that's bad. So you don't want these correlated errors, and this is what was happening in particular due to high energy impacts onto our chips. And we redesigned our chip to sort of be more insensitive to these types of high energy impacts. And that gave us essentially a big boost of 10,000x on this floor, which is now sitting at this 10e minus 10, which is, maybe you'd want to have 1 or 2 more orders of magnitude, but now you're getting into that sort of algorithmically relevant range. So you're sitting pretty good here, and this whole effect is starting to look a lot less scary with numbers like this. So we're pretty happy with this. And then this is sort of where we're going next. Our next milestone is sort of going to be to try to attack this sort of 1e minus 6 error range. So we want to get to this arbitrary line that we draw in the sand here, which is 1e minus 6 error range. And to do this, we're going to need to do 2 things. One, we're going to need to improve our physical qubits. This is analogous to improving our lambda values. And 2, we're going to need to improve the code distance of our system. So we're going to need more qubits and better qubits. And if we do this in some proportion, so maybe we do more qubits, or maybe we do better qubits, we have to do both, but the proportion of it is going to sort of depend. But hopefully we can do it sufficiently so that we can sort of break that barrier here and get below this 1 in a million error range. And by the way, this plot is quite fun because we actually made it in 2023. And it turns out that our experiment in 2024 falls exactly on this, on this line here, or more or less exactly on this line. So we didn't have to remake that plot. We just copy pasted it, added a date 2024 on there, and that was good to go. So that's easy for me, making the slides, but it's also quite a nice statement about the prediction that we made on this slide. So that's cool. Okay, this is usually where I end my talk, or at least this is where I ended my talk in an APS. But we have more time today. Oh, actually, let me summarize this. So this is sort of, if you compare our errors to 2023, you have twice as many qubits, 2x the lambda, 20 times logical fidelities. We have 10,000x lower repetition code floor, which is starting to look a lot less scary. And now we have these real-time decoding. And next step is going to be, again, higher lambdas, more qubits, less errors. And we think that we can actually realize this. We have a budget for the errors that we currently have in our system, and we're going to sort of attack those consequently to try to reduce them. So as I was just saying, this is sort of where I usually end my talk, but in fact, I have a bit more time here. So let's go into more recent and interesting results and talk a little bit about logical operations. And in particular, let's talk about lattice surgery. So we have a big grid of qubit now, in particular a D7 grid. So that means we have a square of 7 by 7 qubits. But if you have a square of 7 by 7 qubits, that means you also have a couple of D3s embedded in there. So you can sort of start thinking about making logical operations between these logical qubits. And this is exactly what we wanted to do. And so in particular, we're going to try to do something called lattice surgery, which is a 2-qubit operations, which allows you to do a measurements on the ZZ quadrature or on the XX quadrature. In this example here, I'm going to be talking about the ZZ quadrature. And before we go into what a ZZ measurement looks like, let me just explain, and this is not showing very brightly, but there's sort of a little blue box here that's sort of different from the rest. And this is sort of a fact about error correction code that is important to note for understanding these things. And the fact is as follow. If you have a line of logical qubits like this, this forms a logical observable. So this is essentially, if you measure the parity of all of these Z, the parity, if you measure Z on all these qubits and you do the parity of this, that essentially gives you the logical Z of your logical qubit. Now, this logical Z is actually analogous to a line of qubit that goes with a slight kink in it, modulo the value of the stabilizer. And this is easy to see because essentially the stabilizer is measuring the value of Z, 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 Z. So it's measuring the parity of all of these qubits that are on the corner of these tiles. And so you're measuring the parity Z, 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 Z. And so if you multiply that in on this line, you can see that this essentially pops these 2 qubit in and removes these 2 qubit out. And therefore, this line here is equal to A times this line over here. OK, are you with me? Yeah? OK, good. OK. Well, OK, let's see. So we're going to use this fact now to claim that when you have a big rectangle like this one here, this logical observable is equivalent to this logical observable modulo all the stabilizers that are in between. And therefore, if I want to know the parity of this one times this one, all I have to do is to know the product of all these stabilizers that are in between here. And you can do this because essentially you can sort of shift these 2 Z's to this place here, and then you can multiply by B. It will give you a line here, and you can multiply by D and C, and that will give you a line here. Multiply by E and F, it will give you a line here, and so on, and eventually you get to this line over here. And so if you want to know what the parity of these two is, again, you can sort of just multiply the product of all of these stabilizers. And this is the quantity you're always measuring. This is what you do in the surface code, is you're always measuring the parity of all these stabilizers. And this is what you do 90% of your time in the surface code. So you know these things very, very well. OK, so now let's use that to build measurements of ZZ. So you start with 2 logical qubits that are separated. Then you start measuring these middle stabilizers here that were turned off. So that means that you start using these new qubits in here and start measuring this parity. And when you do this, you find out that the parity of these ZZ is now the product of these 2 things. And so you've essentially measured this by measuring all these products, and now you can separate them again. And now by doing this operation of combining your tiles together and then separating them again, you have measured the ZZ parity of your qubits. OK, so this is sort of your basic sort of lattice surgery operation. This is what a lot of this quantum computing on these surface codes are based out of. So it's a little crash course in surface codes, but this is how it works. OK, and now let's use this to do something somewhat interesting, which is going to be to initialize a Bell state and then sort of measure that Bell state. And so the way that you do this is you initialize this big patch in a known XXX state. So you initialize all your data qubits in X, so you know from the get-go what this parity is. And then because you're measuring these stabilizers again, it turns out that you also will learn what this ZZ product is. And because you now know what XX is and what ZZX is, that means that you've essentially defined a Bell state. This is sort of the definition of knowing what or one of the definition of what a Bell state is that you know both of these operators here. So when you split these 2 qubits apart, now you have these two logical qubits that are sitting in this Bell state. And now you can sort of chill there for a little while, and you're in this Bell state, and you're smug with yourself. And then at some point, you want to measure it, and so you can do the reverse of it and sort of combine the tiles again to measure the ZZ parity, and eventually measure your X parity by measuring all of your X qubits. Okay, so we've done something very simple. We've created a Bell pair, and then we've measured the Bell pair. But okay, this is still demonstrating all the basic tools that you need for doing lattice surgery. By the way, we affectionately call this experiment the donut experiment. And the reason we do is if you put this in this sort of 3D plane here where time runs in the x-axis, it makes kind of a little loop. And you can track what these observable looks like over time. And remember, you had this X observable that was sort of crossing through this line here. And so if you draw it like that, it starts with this big line, and it's a surface that you can drag in time that splits into these two surfaces here, and then reconnects at the end of your experiment to finally get measured at the end here. So this is one of the observable, the XX observable, that we're going to be tracking through this entire experiment. And then the other experiment that we're going to be, the other observable that we're going to be tracking is the ZZ observable, which sort of, initially you don't know what it is, but as you're measuring all these stabilizers, you start learning what this is, and you start having these two lines of qubits that you can then drag through times until at the very end of your experiment, you sort of measure it by the same process of measuring these stabilizers. And so this is another sort of observable that we want to track in our experiment. Okay, and this is sort of another picture of this, and the only reason I put this in is because these pipe diagrams are probably you're going to start seeing a lot more of them. If you're an experimentalist like me, maybe these are unfamiliar to you, but essentially they represent the same kind of space-time diagram. At the base here, you have this large rectangle, and you drag it forward in time, so time here is going in the z direction. And at some point, they split into these two squares, and then you drag this in time, and they recombine to this big rectangle, and then you go to the end here. So this is the same picture as what was here, but just flip on its head, then stylize it a little bit, and you can have the same observable values plotted in here. And I'm going to make use of this type of pipe diagram to show you something much more complicated in a few seconds, so hopefully that is simple to look at a simple example first. Okay, so we can actually run this on our hardware right now. And the performance are, well, not so great. We get something like 15% errors and 24% errors. But this is all to be expected because this is a complicated experiment. And we're only doing this at a very small scale in these D3 surface code, which means that we're paying the cost of all this encoding, all this overhead that we're doing with all these stabilizers measurement and all this stuff. But we're not really reaping all the benefits of having the larger scale of the surface code, and therefore, we don't expect this to necessarily be better than a 2-qubit gate of a physical qubit. Nevertheless, it's nice to be able to start to do these logical operations, and we're indeed able to do this, and we can sort of justify why these types of error rates by doing sort of a back-of-the-envelope calculation here, where we have roughly 1% error per cycle on these D3s. We have roughly sort of 6 to 8 of these D3 cubes, which gives us about 3% times 6 to 8, which is roughly this 18 to 24%. Okay, doesn't matter, but the point is that the simulation sort of matches the experiment roughly, and we're not sort of way off in terms of order of magnitude. But we're able to start practicing these logical operations, which eventually in the larger computer will obviously be important. So that's all preliminary data, but it's nice to show that we're able to run these experiments. The last thing I want to talk about is the color code. The color code is a different type of code. So we've been talking about these surface code for a very long time now, which is there's these square grids. These color codes are kind of laid out in this triangular shape on this hexagonal lattice. And the first thing that you notice is that because this code is laid in a triangular shape where each edge has a size sort of the distance of the code. So, and for example, here I have a distance 9 code. Well, a triangular shape of distance, d side is smaller than the square of distance d size. And that tells you that you should expect to have less physical qubits for the same distance in a color code than you do in a surface code. So this is quite interesting. And in fact, in the limit of a large distance code, you expect this difference to be about 2x. So you should expect to have twice as many qubits in a surface code, or another way to say it is twice as few qubits in the color code. So you can either have less physical qubits on your hardware, or you can have the same number of physical qubits, but increase your number of logical qubits for the same resource utilization. So that's quite nice. But that's not all. The other advantage of these color code is that you can actually implement a lot of these logical operations in a much easier way. For example, a logical atomar on a surface code actually takes you 3 times the quantum error correction round. And I won't explain why that is, but you know, if d is like 10 or 20, that means this is going to take you tens of microseconds, let's say 50 microseconds. Whereas in the color code, if you want to apply this logical atomar gate, all you need to do is to apply an atomar gate on all the physical qubits, and that takes tens of nanoseconds. So this is orders of magnitude faster than your operation in the surface code, and therefore it's much better for writing algorithms. Similarly, you have something called Y-basis initialization. So on all of our memory experiment, we talked about the X basis and the Z basis. But Y is also a basis that you might want to control your qubit on. And it turns out it's really hard to access in the surface code. There are complex folding protocols that exist that allow you to get this basis in about d over 2 plus 2 rounds. But it's complicated. And at the end of the day, you cannot do lattice surgery on the Y basis, or at least there's no known protocol that I know of right now. And so, but in the color code, you can do measurements and initialization in the Y basis in the same way as your Z and X. So this is really simple. And you can also do lattice surgery in the Y basis. So this is also quite helpful. So operations are also nicer. You need less physical qubits. And now I'm going to tell you about a last piece of algorithm here that is very specific but quite critical. This was developed actually just over the last year or two by a colleague of mine, Craig Gidney, who figured out that you could actually do a magic state injection into the surface code by using a color code at its basis and using the fact that you have all these simpler logical operations. And this turned out to be very, very important. In fact, this type of way of injecting t-states, and remember these t-states are important because they allow you to do non-Clifford gate. This is related to the real-time decoding and all that fun times before. But this is really important, and it was thought for a long time that your quantum computer would basically be spending 90 to 95% of its time just generating these t-states. So this is kind of the bottleneck for quantum computers. And it turns out you can do this about 10 times faster if you make use of this color code and you use this really tricky protocol that Craig developed. And it turns out that in this limit, producing 1 T gates is essentially the equivalent of doing 2 C naught gates. And this is a huge, huge improvement to where we were before. And just to give you a sense of scale, we're going to use our pipe diagram knowledge all over again here. And we're going to look at these diagrams. These diagrams are pipe diagrams, which means that the surface area of these pipes here is 1 patch of surface code. And this used to be the way that people thought you would generate 1 T-state. So you had to do all of this work over all of this quantum computer, over all of this time on the z-axis to essentially give you 1 T-gate. So this is obviously very expensive. And it turns out that over time, people figured out ways to do this easier and more compactly. But this latest method that uses the color code is tremendously smaller than everything else that came before it. And this is a huge, huge, huge improvements to where we were before. And so just for that purposes, studying the color code is important. OK. So now that I've said all these nice things about the color code, let me give you the downside of it. So what's the catch here? Well, the catch is that you need to do these stabilizers that are much higher weight. So these weight 6 stabilizers, instead of these squares, you now have these hexagons. And the circuit for measuring these hexagons is a little bit deeper and is a little bit more error prone. So you're going to have more errors per quantum error correction cycle. And then at the same time, The decoding algorithms are a bit less advanced, and this is because surface code decoding uses something called matching decoding, and that works really fast. You can do really fast decoding that way, but it doesn't work with the color code because essentially you have sort of 3 correlated graphs instead of 2 correlated graphs. This doesn't matter what that means, but for those experts in the room, they'll understand what I mean with this. And so, yeah, basically, decoding is harder. You have more noisy stabilizers, and therefore, it's harder to implement below threshold than it is for the surface code. Nevertheless, this is what we did. And so we have this, this memory experiment that actually demonstrates that we can do below threshold experiment on the color code. So we compared the D5 surface color code to a D3 color code, and we showed that we were able to suppress the errors by increasing the size of our code. And our lambda value here is 1.56, so not quite as good as the 2.14 that we got in the surface code, but still quite respectable. And in fact, it's still below the qubit, the color code threshold. And so that's really, really cool. And in fact, although right now this code is not outperforming the surface code, we think that as we increase the hardware, it's possible that at some point this code actually outperforms the surface code, and we may start using it more. So this is very cool. We can also run these lattice surgery experiments. In this case, again, one of these pipe diagrams here, but now you have these triangles instead of these squares at the base. Yeah, you can do lattice surgery again on this color code. In this example here, we did a teleportation experiment where we take a logical observable here, we do lattice surgery, and it teleports the observable to the other qubit here. And this is sort of depicted in this diagram here, which is more or less just lattice surgery and doing that post-processing, essentially feedback on it. And so, at the core of it is just the experiment of lattice surgery. And so we can do this, and the state fidelity, again, are not amazing, but they're still decent, and that's good to see. Now, there's a couple more things that we can do with this. We can do logical Clifford gates, and to demonstrate that, what we did is a logical randomized benchmarking experiment. So you may be familiar with sort of physical randomized benchmarking experiments. This is sort of a logical version of it, which is kind of fun to do. And similarly, we can do sort of magic state injection. This is the first step to this cultivation algorithm. So this is not the whole cultivation algorithm, but it is a first step to it. And we can show that we can inject an arbitrary state on this 1 qubit here, and then kind of expand it out to this whole patch of color code. So in that way, we can inject an arbitrary state into our logical qubit, and we can do this with a high fidelity. So between all these results, it makes for a really interesting sort of future for the color code. Of course, we're still sort of using the color code as the surface code as our main workhorse for most of our experiment at Google. But this is a really good candidate for future sort of improvements on this, and it just shows you the space of possibility that goes beyond just improving your hardware. You can also improve how you control and how you use your qubits to make your algorithms better. And what that's really showing you is that we're kind of improving things from two ends, right? We're making our hardware better from the bottom up, and we're also lowering the cost of quantum computation from the top down using all these nice algorithms like the cultivation protocols, like using the color code instead of the surface code. And hopefully these two things kind of meet at some point in the middle, and we can actually realize some of these quantum algorithms. And so with this, I'll leave it out for a question, and thank you for listening. Uh-huh. Not so much. I think like these rep code results, the reason you see a floor is because you see these high energy event correlated events, right? So so it's not so much about the bias of these errors, and by bias, I would mean it means something more like, is it more T1 error or T2 errors? You see a little bit of both of these things, but it all goes bad for these qubits. Basically, T1 goes bad, T2 goes bad at the same time. And the thing that's bad is it goes, as a correlated fashion across the whole processor. So that's basically what it is. It, Oh, concatenated red both. I think it would depend on how separated your physical qubits are in space, right? Because these events are physically sort of correlated in space. And so if you had them, for example, in two modular chips, you can imagine that like, having a concatenated code between those two modules would help you. But if you have them both sort of on the same chip, sort of right next to each other, then maybe that event would sort of ruin both of your logical qubits, and therefore that wouldn't help you that much. Um, yeah. But at the end of the day, the solution that we end up with here is that really, making your physical qubit more insensitive to this noise is essentially sort of helping you out a lot, and perhaps there's even some more gains to be had there. And if you can get below, 10 to minus 12, then who cares? I'm not even sure I could measure anything that's below, 10 to the minus 12. I mean, we're talking about even for these 10 to the minus 10 events, this is something that's happening once every couple of hours. And so if you start to do this 100 times or 1,000 times lower than this, you're going to have one event happening every couple weeks to couple months. And at that point, does it even matter if you can run your experiment within the time taken? In fact, there's always going to be a floor, right? Like your classical computer has a floor too. For example, I live in Southern California right now, and if there's a big wildfire in the area, it will bring down my classical computer desktop at home, and so that imposes a floor on the computation of our experiment. So the question is that floor sufficiently good to run an application? That's really what you care about at the end of the day. Yeah. Yeah. So there's two things to say about this. One, the first thing is that when this high energy event sort of hits your chip, it creates these quasi-particles throughout your whole chip, and they kind of propagate across. And so they propagate across the surface of your chip, so they're not sort of, they don't necessarily follow a trajectory. Sometimes you can maybe try to see a streak in your processor and that kind of stuff. But this is kind of probably besides the main point that I want to make, which is that this term that I use, which is high energy event, is actually the correct term. And people are sometimes referring to them as cosmic rays. And that is one source of high energy particles, but you also have radioactivity that's coming from inside the house, right? It's, inside your chip, you have these materials that are radioactives. And so that you can't really shield too much against, right? Because they're really coming from inside your experiment itself. And so, trying to protect yourself against that is hard, but making yourself more insensitive is really kind of the better way to go about this. Yeah. Mm-hmm. Yes, that's an excellent question. That is one of the challenge of building these systems. This is a hard classical algorithm problem, and at the end of the day, you can parallelize these algorithms. You can do all sorts of optimization on them. But it is true that increasing the size of the code makes this problem of decoding harder. The other thing that I will say though is that decreasing the number of errors that you get per cycle makes the problem easier. So what actually matters is how many errors you get in total over your whole processor size. So as you increase the number of qubits, that makes your problem harder, but as you make your number of errors better, it makes your problem easier. And so there's sort of a, as we go on in our progress and we make our qubit better, that actually helps you out in some way. So yes, we'll have to improve our classical algorithms, and yes, there's also some hope of making that happen. So yeah. You're saying like, how are we going to continue scaling with the surface code or switch to an LDPC code or something like that? Mm-hmm. Right. You need more physical qubits. Yeah, yeah. So we're just going to scale the number of physical qubits ultimately. Yeah, yeah. So ultimately, we can have much more than two. You just need more physical qubits. On our current chip, on our 105 processor, that's the most that we can fit on there. But as we increase the number of qubits on our chip, if we make it, 1,000 qubits or 10,000 qubits, then you're going to have a lot more space to put more logical qubits on this chip, and now you're going to be able to do operations with more qubits. You are indeed right to point out that there are other codes alternative, like for example the LDPC code that you mentioned, or the color code that we just talked about here. And those are all valid approaches to this problem. Yeah, no, with the surface code can work as well. There's no fundamental limit to how much you can scale it, except your ability to engineer a system that has thousands of qubits or 10,000 qubits. This is a hard engineering problem, but that's why we have smart scientists and engineers doing these types of work. Yeah.
We're right at time, so please join us for lunch. If you have more questions, you can ask Alex. You guys call them pipe dreams?
I love that. I hadn't heard that one before. No.
Yeah, pipe dreams. And like, the Microsoft screensaver?